Hi everyone. Having in the last video learned the definition of the Riemann integral and worked through a couple of examples, we now want to move into a characterization of Riemann integrable functions. In particular, in this video, we will first establish an equivalent definition of Riemann integrability, and we will then prove two theorems related to showing that certain classes of functions are in fact Riemann integrable. The first result that we want to prove is theorem 2.36 in the book, which is you can think of it as an alternate criteria for Riemann integrability. So the theorem says let f be bounded on the closed interval AB. Then f is Riemann integrable over AB if and only if, given an epsilon greater than 0, there is a partition P such that the upper Darboux sum of f over P minus the lower Darboux sum of f over P is less than epsilon. Now, we will prove this theorem, but before we do, right, notice that logically, right, this is an if and only if. And so what we're saying really is that the definition of Riemann integrability is logically equivalent to this alternate condition. So in some cases later on, in fact, later on in this video, we will actually show that a given function satisfies this condition and then use that to say that the function must be Riemann integrable. Now, just sort of analyzing this claim first, you'll notice that one of the advantages of this, if you think about the definition of Riemann integrability, Riemann integrability requires you to calculate the upper Riemann integral and the lower Riemann integral and show that they are equal to one another. Notice that this condition only deals with sums, right? So the nice thing here is that this doesn't actually require us to take any infimums or supremums. We can actually work directly with the upper and lower Darboux sums themselves. And so this is really a condition on the upper and lower Darboux sums without having to take infimums and supremums, but we can still establish Riemann integrability. So this is often a slightly nicer criteria to work with in a technical sense because it doesn't require us to pass to infimums or supremums of sets. We can actually just work directly with specific upper and lower sums over some partition. To think about proving this, so we have an if and only if. To prove an if and only if, we need to prove both directions. So we will start then by first proving the forward direction. All right, so in the forward direction, what are we doing? We're going to assume that our function is Riemann integrable, and we want to show that given an epsilon greater than 0, there exists a partition P such that this condition is satisfied. Okay, suppose f is Riemann integrable. And we need to show that this condition holds for any arbitrary epsilon greater than 0. So let's take an arbitrary one. So suppose f is Riemann integrable and let epsilon greater than 0 be given. Okay. Our goal is now to find a partition P such that this condition is satisfied. All right. So since our function is Riemann integrable, that tells us that the upper Riemann integral and the lower Riemann integral are equal to each other, and that is in fact the value of the Riemann integral. So let A, we're going to call A the value of the Riemann integral of f, which is of course equal to the lower Riemann integral and the upper Riemann integral. Right? These equalities hold because we are assuming that our function f is Riemann integrable. And sorry, I've written 0, 1 here, but this should be the arbitrary interval AB. All right. So now if we look at the lower sum first, since A is equal to the value of that lower Riemann integral, and that is defined to be, so the lower integral is the supremum over all partitions of the lower sum of f over those partition. If I look at this definition, since this is the supremum, well, what does that mean? That means that if I look each of these lower sums, right, they are increasing, and the supremum is the least upper bound, right? So by taking particular partitions, I ought to be able to get as close to that least upper bound as I like. So since this is the case, I ought to be able to choose a partition. I'm going to call it P1. So that if I look at the difference between A and the lower Darboux sum of F over P1, so notice that, right, A, because it's the supremum of all these things, it's an upper bound, it's always going to be greater than or equal to any one of the particular lower sums. But I can choose this so that this difference is as small as I would like, because A, this is defined to be the supremum of all of these things. So I can choose a particular partition that gets as close as I would like to this. I want to make it within epsilon over 2. Okay. So I'm choosing this particular partition P1 so that A minus the lower sum of F over the partition P1 is less than epsilon over 2. They're within epsilon over 2 of each other. Okay. All right. Now, similarly, I want to choose a partition P2 so that, now I basically want to do this for the upper sum. So I could change all of this. A is also equal to the upper Riemann integral, which is equal to the infimum of P over all the upper sums. So I can choose a P2 so that the upper sum of P2, comma F, minus A, so the difference between the upper sum of F over this partition P2 and the actual value of the integral is as small as I would like. I'll make that less than epsilon over 2 as well. All right. So now I'm going to choose, notice I've sort of been very careful to call these P1 and P2. My goal is to find a partition P such that this difference is less than epsilon. So I'm going to now choose P to be equal to the union of P1 and P2. So said another way, P is the common refinement of P1 and P2. I've taken these two different partitions, and I'm now going to create a new partition by taking all the points that were in the first partition and all the points in the second partition and throwing them all in together, right? Okay. So one advantage of this is that now P is both a refinement of P1, so P contains all the points of P1. It's also a refinement of P2. So it contains all the points of P2. So we call P a common refinement of P1 and P2. Well, let's see what happens then. Okay, so what happens then if I look at the upper sum of PF minus the lower sum of PF? Well, first of all, P is a refinement of P2. And so since P is a refinement of P2, we must have that the upper sum, remember, as we refine partitions, our upper sums get smaller. So the upper sum of P must be less than or equal to the upper sum of P2F, because P is a refinement of P2. Okay, so if we replace this with P2, we're going to make this difference larger. Now, on the other hand, it goes the other way with lower sums. So we looked at this at the beginning of the previous video. Okay. So here, as we refine, our lower sums get larger. So what's happening here, right? If you look at this, you've got upper sum of F over P, lower sum of F over P. But now you're going to make the upper sum, so you have upper sum of F over P, lower sum of F over P. Now what you're going to do is you're going to swap out, and I just realized here I wrote P2 and I should have written P1 here. Now what we're going to do is swap out the P here for P2. That's going to make the upper sum bigger. We're going to swap out the lower sum with the P here for a lower sum of P1. That's going to make this bigger. That's going to make the difference. So we're making the U piece larger and the L piece smaller, and that's going to make the difference larger. So this is less than or equal to UP2F minus L P1F. Well, now if I take this and I add and subtract A in the middle, I'm actually going to subtract A and then add A. I get this, and now grouping these terms, I see that the quantity in the first set of brackets I know to be less than epsilon over 2. In the quantity in the second set of brackets, I also know to be less than epsilon over 2. And so this entire quantity is less than epsilon over 2 over epsilon over 2, which is epsilon. So notice I have successfully here proved the forward direction. I've shown that if I take a Riemann integrable function, I can always find this partition P. I've constructed it here by constructing this partition P1, this partition P2, taking their common refinement to get P. But I've now shown then that with this partition P, the difference between my upper sum of F over P and my lower sum of F over P is strictly less than epsilon, which was arbitrary. So I could do this for any epsilon. Now notice what really sort of makes this tricky is the fact that because of the definition of the upper and lower Riemann integrals as infimums of upper sums and supremums of lower sums, right? Here I could find a partition P1 so that my lower sum got as close to the value of the integral as I would like. I could do the same thing with upper sums. The problem was I couldn't guarantee that they were the same partition, right? I can't guarantee that the partition that gets my lower sums within epsilon over 2 of A is the same partition that will get my upper sums within epsilon over 2 of A. So I have to assume that these are different partitions, and then the work is to show that, oh, okay, but I can then take their common refinement, and that is a partition such that the upper and lower sums will both be within epsilon of each other. Okay. All right. It turns out the forward direction is, in fact, the more difficult of the two directions. So the reverse implication is actually a bit easier. Okay, so it's always nice when we've already gotten the hard work done, and we can proceed a little more quickly with the reverse direction. So as we start to think about the reverse direction, now we're not assuming that the function is Riemann integrable. We're assuming that this condition about the difference between the upper and lower sums is satisfied, and we want to use that to prove that our function must be Riemann integrable. So in the reverse direction here, let's suppose that we have our function f. Our function f is bounded, and we're going to take an arbitrary epsilon greater than 0. So let epsilon greater than 0 be given. Okay. Then our assumption here, right, is that we can find a partition such that the upper sum of f over p and the lower sum of f over p differ by less than epsilon. Okay, so choose p such that the upper sum of pf minus the lower sum of pf is less than epsilon. Okay. However, I want you to note that, right, the lower sum, this particular lower sum, right, this is always going to be less than or equal to the lower integral of f over AB, right? Because this is defined to be the supremum of all quantities of this type. So the supremum of all of these things must be less than this particular one for this particular partition. Okay. And these must always be less than or equal to the lower Riemann integral must always be less than or equal to the upper Riemann integral. And the upper Riemann integral is the infimum of all the upper sums, so it must be less than any particular upper sum. So it must be in particular less than this. Okay. Now, if we look at this whole thing, we're really going to sort of look at this in two parts. But I guess the easiest way to think about this is the difference between these two must be larger than the difference between these two, right? Think about how these are ordered. So this minus this must be a larger difference than this minus this. So what we have is that the difference between the upper integral of f and the lower integral of f, this must be less than or equal to any particular upper sum minus any particular lower sum. Okay. But we've chosen these. We chose this partition such that this difference was less than epsilon. Okay. And so now what have I shown? I've shown that the difference between the upper Riemann integral and the lower Riemann integral is less than epsilon. But epsilon was arbitrary, so I could do this for any epsilon. So what number here could possibly be less than every positive epsilon? This only works if this quantity is 0. Okay. So since epsilon greater than 0 was arbitrary, it must be that difference, the difference between this upper sum and the lower sum, must be 0. But what does that mean? That means these two things are equal, which means the upper Riemann integral and the lower Riemann integral are equal. That means the function is Riemann integrable. So f is Riemann integrable, which is what we wanted to show. All right. So now we've established this alternate criteria for Riemann integrability. Again, the advantage of this is it allows us to not have to always work. We're sort of improving this theorem. We're doing the hard work of figuring out how the infimums and supremums affect things. And now we can really just work by finding particular partitions and showing that we can find a partition so that our upper sum and our lower sum are arbitrarily close to one another. All right. So armed with this sort of new tool, let's now see if we can prove that some certain classes of functions are Riemann integrable. And as I mentioned at the end of last video, the first and most natural to hope for, either because we've sort of seen that this should be the case in a calculus course, or intuitively you just want to start with a nice class of functions, you sort of wonder, well, are all continuous functions Riemann integrable? Okay. And they are, in fact. So our goal next will be to prove this theorem that if f is continuous on the closed interval AB, then f is Riemann integrable on the closed interval AB. Now, the first sort of thing to say is, right, if this function is continuous on the closed interval AB, we need to keep in mind we know a lot of things about continuous functions on closed intervals. The intermediate value theorem holds, right? The extreme value theorem holds. A continuous function on a closed interval must be bounded. A continuous function on a closed interval is uniformly continuous, right? We have sort of all these facts. Now, we're not going to need to use all of them, but we need to know sort of, anytime you're approaching a problem like this, it's nice to look at this and say, okay, I'm going to get to assume f is continuous. What do I know about continuous functions? So it can even be helpful to sometimes write down just a list of, sort of a list of tools that you have at your disposal if you need them. Okay. All right. So my goal is going to be to show that f is Riemann integrable, and I'm going to use this new criteria to help me prove that this function is in fact Riemann integrable. All right. So if I'm going to use that criteria, what do I need? I'm going to need to show that I can find a partition P such that the difference between the upper sum of f over P and the lower sum of f over P is less than any given epsilon. So let's start with an epsilon. Now, let's see. I'm going to start by using the fact that if f is continuous on this closed interval, then f is uniformly continuous on this interval. So since f is continuous on the closed interval AB, then f is uniformly continuous on AB. Now, what does that mean? Okay, so how am I going to use uniform continuity? Well, uniform continuity means that then I can pick a delta. Already got an epsilon. So there exists a delta greater than 0 such that whenever x1 and x2 are two values in my closed interval AB, and x1 and x2 are within delta of each other, we have f of x1 minus f of x2. I can make this as small as I'd like, so I can make it less than epsilon. I'm actually not sure right now how small I might need it to be. Let's just leave a placeholder here. And we'll figure that out along the way. But for now, we've sort of got this as a tool at our disposal. I can make that as small as I want. So I can, make it less than epsilon, make it less than epsilon over 2, epsilon over 53. Like, let's see what we need this to be as we proceed with the rest of the proof. Okay. So what I'm going to do is I'm going to choose a partition P. With the norm of the partition being less than delta. Now let's remember, this is really the first time we've used this norm concept since we defined it. So what does that mean? The norm of the partition is the largest subinterval on the partition. Okay, so the norm of this partition, what I'm saying is that the largest subinterval has a length that's less than delta. So really the way I want to think about this is if I choose a partition P with norm less than delta, that means each of my little subintervals has length less than delta. Okay. And you might be starting to see, oh, that'll be nice because if I take two x values out of the same subinterval in the partition, then they will be within delta of each other because the norm of my partition is less than delta. And then I can make f of that x value and minus f of that other x value within any quantity I want of each other. Okay. So let's choose a partition P. Again, we're basically just choosing it so that no 2 points in the partition are more than delta apart. Okay. If we do that, let's see, then what do we get? Then if I look at the difference between the upper sum of f over p and the lower sum of f over p. Okay, what is that? Well, the upper sum of f over p will be that. And the lower sum will be this. Okay, and I noticed that I could combine these sums, right? So I could combine these together, and maybe I'll here. I could write this as capital M sub k minus little m sub k times delta x sub k. Now, recall that the function f we're working with, it's continuous. Okay, since it is continuous, this capital M sub k, right, it's defined to be the supremum of the function over the kth subinterval in the partition. But this is a continuous function, which means it actually achieves its supremum and its infimum by the extreme value theorem. Okay, so by the extreme value theorem, there are points I'm going to call them x1k and x2k. Now they are going to live again in that kth subinterval, so between x sub k minus 1 and x sub k, such that f of x sub 1k is equal to capital M sub k, and f of x sub 2k is equal to little m sub k. So what I'm doing is, right, I have this partition of AB, and I have sort of all these points, but let's sort of imagine we zoom in here to one particular little subinterval, okay? And my function is doing, whatever it does up here, okay? What I'm doing is saying if I'm going to construct the lower sum here, because this is continuous, there's actually going to be a value where I achieve my minimum. That's what I'm calling x sub 2k. And a value where I achieve my maximum. That's what I'm calling x sub 1k. And again, because of the way I've chosen my partition, with the norm of the partition being less than delta, this whole subinterval has distance less than delta, which means these two things are going to be within delta of each other. That's going to become important in just a moment. All right. So let's see what happens then. So if I sort of come, I'm going to write a little bit out of order. If I come back up here then, okay. So using this fact, I can replace this. This is the sum k equals 1 to n of f of x1k minus f of x2k times delta xk. So I'm just replacing x sub 1k is where we achieve the supremum of f over the kth subinterval. I'm just going to write capital M sub k as f of x sub 1k. Okay. Now, erase this so we can continue with this line of thought. Now, if I look at these two, I said just a minute ago, right? These two x values, they lie in the same subinterval of the partition. That's the way we chose them. And each of my subintervals has width less than delta. So these two x values are within delta of one another. They also both lie in AB. So f of x sub 1k minus f of x sub 2k in absolute values, right, has to be less than whatever quantity I put in this box. Okay. So now I'm going to go ahead and fill this in, and we'll see exactly why this is going to work in a second. I'm going to make this quantity epsilon divided by b minus a. So that if I do this, right, this will be, sorry, strictly less than the sum k equals 1 to n of epsilon over b minus a times delta xk. But this is equal to the epsilon over b minus a is a constant as far as the sum is concerned. So this is epsilon over b minus a times the sum delta xk. But this sum, this is just the sum of the lengths of all the subintervals. It must add up to the whole length of the interval. The interval is AB, so this is going to be just b minus a. So this whole quantity here ends up being equal to epsilon. So what we've done here is we have constructed a partition such that the difference between the upper sum of f over that partition and the lower sum of f over that partition is equals less than equals epsilon. Okay, so this difference is strictly less than epsilon. In order to do this, the important properties of f, I mean, certainly that f was continuous, and the properties that follow from that is that f is uniformly continuous on this closed interval, and also the extreme value theorem. Those both end up being critically important results to then establish that all continuous functions are Riemann integrable. So again, we've actually shown that this alternate criteria for Riemann integrability is established, but previously we showed that that was equivalent to Riemann integrability. All right, so this is nice. This gives us that all continuous functions are Riemann integrable. And a nice thing to sort of start to recognize here is that this is the first sort of glimpse you get that in some sense, integration is nicer than differentiation, right? Not every continuous function is differentiable, right? The absolute value of x is a continuous function, but it is not differentiable at 0, right? But the absolute value of x, because it is a continuous function, we now know it is Riemann integrable. So it's sometimes nice to have this visual a little bit in your head of sort of how these sets of functions are related to one another. So if you sort of think about, you have here all the differentiable functions. Well, we know that the differentiable functions are a subset of the continuous functions, right? Every differentiable function is continuous, but not every continuous function is differentiable. Okay. So you have this larger set of functions, which are the continuous functions. And we've now shown that every continuous function is Riemann integrable. I guess a question that remains, we don't know, maybe it's possible that the Riemann integrable functions are precisely the continuous functions. It turns out that that's not true. You can have discontinuous functions which are Riemann integrable, and we'll look more at that a bit later. So we certainly know that the continuous functions are a subset of the Riemann integrable functions. That is what we've just established. That they are a proper subset, we haven't quite established yet, but we'll add up here the Riemann integrable functions. Now, in some ways, this picture is a little bit of a lie, because it gives a sense, like, as I've drawn this, you might think like, oh yeah, about a quarter of Riemann integrable functions are differentiable. If we were going to actually draw a sort of to scale version, you should really think of like the set of Riemann integrable functions as being a plane, the set of continuous functions as being some line in that plane, okay, and the set of differentiable functions as being some dot on this line in this plane. And the reason this is a little more accurate is if you had a big, if you could sort of imagine you have a hat that's filled with all the Riemann integrable functions, and you reach in and you pull out a function, you could ask yourself sort of, well, what's the probability that I pull out a continuous function? The answer is essentially zero, right? The set of continuous functions, it's sort of like saying if I were to throw a dart at the plane here, what's the chance I hit this green line? Well, this is a line. It has, a sort of zero thickness. So the chance that you actually hit this line with a dart thrown at random is essentially zero. Similarly, if you throw a dart randomly somewhere on this line, what's the chance that you hit this point? Again, it's zero, essentially. This has zero width on this infinitely long line. So while this is sort of a nice way of just conceptualizing what is a subset of what, in terms of how frequently these things occur, this is a much more accurate depiction. The set of differentiable functions in the set of all continuous functions is a very sort of rare in a certain way type of set. These notions can be made more precise, again, using more analysis. And when you study measure theory and measures of different sets, while we will broach this a little bit in 5620 analysis 2, we'll mostly be looking at measures of subsets of R, not, say, a measure of a set of functions. So we won't get quite as much into this, but I think it's worth, having a concept that as much as we think about in calculus, like all of these different functions, most of the time we're looking at functions which are differentiable. They're actually quite rare. And so we should just be aware of that and not draw too many generalizations about the functions we typically work with and we shouldn't try to extrapolate them to all functions or all Riemann integrable functions or even all continuous functions, because trig functions, polynomials, almost all of them are like differentiable on their domains. So they're actually really special functions that aren't representative necessarily of functions at large. Now, the last result we want to show is we want to look at one slightly different class of functions, the class of monotone functions. So again, to just remind yourself, a monotone function is a function that's either always increasing or always decreasing. So we typically will specify and say monotone increasing or monotone decreasing if that's important. But monotone just means, right, that it's either always increasing or always decreasing. It actually turns out that all monotone functions are integrable. This is interesting because monotone functions are not necessarily like any proper, there's no proper containment either way between monotone functions and continuous functions, right? So this function is a monotone function despite the fact that it's not continuous. right? So certainly not every monotone function is continuous. Not every continuous function is monotone, right? So this is just sort of a different class of functions we can think about, but still be able to prove that they are integrable. Now, I will point you, if you go back to, we're going to go through this proof, but if you go back to the previous video, there is, we worked through the example of the integral from 0 to 1 of x cubed dx. X cubed is a monotone function. We actually are going to use a lot of the same ideas. So if you find this a little confusing, maybe go back to that previous example, look at that, think through that, and then come back and rewatch this proof. Because that provides some grounding in a particular example that can sometimes be helpful if the more general case here seems a bit confusing. So let's prove this. So without loss of generality, I'm going to assume that my function is monotone increasing. The proof is nearly identical if it's monotone decreasing. So without loss of generality, assume that my function f is increasing on AB. All right, I want to show this is integrable. I'm going to use my alternate criteria for Riemann integrability. So I need an epsilon. So let epsilon greater than 0 be given. Okay. Now, similar to, again, to what we did with the x cubed example in the previous lecture, I'm going to choose a particular partition. So I'm going to let P be the partition A plus delta x, A plus 2 delta x, so on and so on, up until I get to A plus n minus 1 delta x, and then finally B, where delta x is just the quantity B minus A over n. So I'm just taking a uniformly spaced partition. It has n plus 1 points, which define n subintervals, each of length B minus A over n. So I'm just splitting this interval up into n equally spaced subintervals. Okay. Again, same thing we did in that x cubed example. All right. Since f is increasing, just as we did with x cubed, on any one of these subintervals, the maximum value of the function on that subinterval, or should say the supremum, must occur at the right-hand endpoint. Okay. So this maximum value must occur at the right-hand endpoint. So this would just be f of xk. And the minimum value must occur at the left-hand endpoint. Now, if we consider, and sorry, I wanted to call this P sub n, right? This depends on how many things I take in my partition. So that makes you think of this as defining a whole family of partitions here. For each n, I get sort of a slightly different partition that just has more points in it. So if I consider then the upper sum of P sub n f minus the lower sum of P sub n f, right? What is this going to be equal to? So this is going to be the sum. I'm going to drop off. These are all going to be k equals 1 to infinity. So this is just going to be an m sub k delta x sub k minus a sum little m sub k delta x sub k. And now here again, I know this, so I could combine these, so I would get a capital M sub k minus little m sub k times delta xk. I know what these are, right? So these are just f of xk minus f of x sub k minus 1. And this delta xk is just this b minus a over n. And what I want you to notice is that this doesn't depend on, this is a sum over k, right? These are all sums over k. This doesn't depend on k, so I can pull this out of the sum. So this will be equal to the sum, oh, sorry, this will be equal to, pull that out of the sum. So this is b minus a over n times the sum over k of f of x sub k minus f of x sub k minus 1. Now, if I look at this sum, okay, this is what we call a telescoping sum. So if I start writing out when k is equal to 1, this is going to be f of x1 minus f of x0. When k is equal to 2, this will be f of x2 minus f of x1. But in the previous term, I had a plus f of x1, so the f of x1s are going to cancel. When k is equal to 3, I'm going to have a f of x3 minus f of x2. Well, now I have a minus f of x2, and in the previous term, I had an f of x2. Those are going to cancel. And so what happens is, as you add this sum up, so the b minus a over n remains, there are only two terms that don't get canceled out. It's the 0 term. So when k is equal to 1, you get a minus f of 0 here that never gets canceled out. And when k is equal to n, you get f of xn that never gets canceled out. So you get an f of xn, but xn is just the last value in my partition here. So I get an f of b minus a f of x0, but x0 is going to be the first point in my partition, a. And so I get this quantity here for the difference. Okay. Well, now notice, if I look at this, what happens as n goes to infinity? As n goes to infinity, this is a fixed quantity, this is a fixed quantity, and I have an n in the denominator. So as n goes to infinity, this term is going to 0. Okay. So since the right-hand side goes to 0, as n goes to infinity, well, that means I could always find a partition that's smaller than any epsilon. Okay. So since the right-hand side goes to 0 as n goes to infinity, we can find an n greater than 0 such that the upper sum of P in F minus the lower sum of P in F. This difference is going to 0. So if I go out far enough, it certainly has to get less than whatever this epsilon was up here. Because if it never got less than that epsilon, it couldn't go to 0. So it must get less than epsilon because it's going to 0. Okay. But then this P sub nf is exactly the partition so that the upper sum of f over Pn and the lower sum of f over Pn are less than epsilon. And so hence f is Riemann integrable. So here we did not need to use continuity. We simply needed that the function was monotone in order to establish Riemann integrability. So again, this is once again giving us another class of functions which are Riemann integrable. Again, that class of functions is larger now, we know, than the continuous functions. We also know it's larger than the set of monotone functions. So actually, there are quite a lot of functions, relatively speaking, which are Riemann integrable when as compared to, say, example, all the functions that are differentiable. Now, once we have this, we have some understanding of what differentiable functions are, what integrable functions are. We understand the definition. We have some criteria that we can use to help us establish this. We know some examples of functions that are Riemann integrable. And now the question becomes, okay, can I use all of this to start proving some of the standard things we did in calculus, right? So the first thing would just be, can I prove that the integral of a sum of two functions is the same as the sum of the integrals of each respective function? In the next video, we will look at some of those algebra of integral types of properties. After that, however, the big thing that remains is we still really don't have a good way for calculating the actual value of an integral. And in calculus, you will remember that we had the fundamental theorem of calculus. So within a couple of lectures, our goal will be to prove, among other things, the fundamental theorem of calculus in order to aid us in actually calculating the values of integrals.